In this video, we're going to continue talking about physical applications of the integral. And we're going to talk about it in the context of work. Specifically, I'm going to do some stuff with springs here. The general idea will be able to be applied to other contexts other than springs, and we'll see that a little later. So our goal is that we want to find the work done on an object when a force is exerted on the object to move it some amount of distance. And in like an intro physics class, if you're referring to a constant force, this is pretty easy to deal with. The definition of work is that it's force times distance. And so this really isn't that difficult, but once we end up with a variable force function, things can get a little bit trickier. So let's pretend that we have this variable force. My arrow is getting smaller. We'll pretend that this is the force being exerted, and the gradient in color is representing the change in force, as well as the size of the arrow as we kind of move through it. So this is a bad way of representing force across a distance, but whatever, it's good enough. We're going to apply the slice and sum strategy. We'll cut this into some sections, and on each section, we're going to assume that the force function is constant. So then what we can do is we can take a look on the work on the kth section, and that's going to be the force function at some x sub k star times whatever the distance is, and the distance will be our delta x. So we just pick some representative, maybe right here. We take whatever the force is at this point, pretend that that's the force on the whole subinterval, multiply it by delta x, and that's our work on that subinterval. We can approximate it that way, whatever. So then we'll say the total work is the approximation, or is approximated by summing all of these up. And then once we get to applying a limit as n goes to infinity, and then delta x gets really, really small, we'll take a look at the sum of these things. And this turns into a definite integral from, we'll say, a up to b of whatever our force function is, evaluated at not just some picked points from each subinterval, but across all the x values on this whole interval. And then we have our delta x turning into this differential dx. So here we go. The work done by an object, or on an object, sorry, by a variable force. With that force function f, if we're moving along a line from x equals a to x equals b in the direction of the force, this is what we've got. Not too big of a deal. This feels a lot like our density problem that we had, where we were trying to figure out mass. It's really, really similar because we still have this kind of product of a function times a distance. When we talk about springs, we're going to use Hooke's law specifically. You may have seen this in some physics courses. If not, this is what it is. The force needed to extend or compress a spring by some distance x is a linear scale of the distance. And so what that means is that force is just some constant k times x, where that k is going to be constant for a specific spring. So if you're only considering one spring, you have a spring constant for that spring, and the force that you're going to need to exert to stretch or compress that spring some distance is going to be k times x. So we can jump into an example then, and we can say, let's suppose that we have some force, 5 newtons in the negative direction. We're going to be required to use that to compress our spring 0.2 meters from its equilibrium position. So since we're compressing this, we'll say this is like a negative force. That's what we mean by negative direction. And since we're compressing this thing, we're going to say x is actually equal to negative 0.2. Our distance that we've moved is going to be backwards 0.2 meters. And so if we're thinking about Hooke's law, we can find the spring constant for this spring by just saying negative 5 newtons is equal to k times negative 0.2 meters. And so k is going to be negative 5 divided by negative 0.2. This is going to be 25. So we have our spring constant, which then gives us our force function for this spring. Oops, I wrote 2k on accident. There we go, 25x. Now we can take a look at the second part of this. How much work is required to stretch the spring 0.5 meters from its equilibrium? So we're starting at equilibrium, 0. We're going out to 0.5 meters, and we're going to use this force function and we can integrate this thing. Because again, work is just our integral of our force function. So this isn't a hard integral to do. 25x squared over 2 evaluated from 0 to 0.5. Evaluating at 0.5 means that we've got 25 times 0.25, over 2 minus 0. 25 times 0.25 over 2, that is 25 over 8. So a little bit bigger than 3, right? 3 1/8 or something like that. But that's the work that we're going to be applying. We could keep track of our units here, and since we're looking at newtons and meters and all this stuff, I think our work unit is joules. Is that right? I don't remember. I'm not a physicist. We could keep track of all that stuff if you'd like. Follow-up question. How much work is done when the spring is stretched another 0.1 meters? So we still have the same force function because we're still looking at the same spring. It was 25x, right? Yep. But now what you're going to notice is that our integral isn't going to go from 0 to 0.1. No. What it's doing is it's saying we're starting where we left off. We left off at 0.5 meters. So we're going to go 0.5 meters up to 0.6 meters because we're going another 1 meter. And so again, we can integrate this, and it ends up being pretty easy to do. Evaluate this from 0.5 up to 0.6. Oops, that looks like a 6.6. And we've got 25 times 0.6 squared over 2 minus 25 times 0.5 squared over 2. So what's this? That's going to be 0.36 divided by 2, so that's 0.18. So this is 25 times 0.18. Minus whatever that was, 25 over 8. And this one I think we're going to get 9 over 2, right? Minus 25 over 8. So we could say that's 36 over 8 minus 25 over 8. And we end up with 11 over 8. So these spring problems aren't terribly difficult. We're going to use Hooke's law. If you've not seen that before, try and commit that part to memory. We'll use Hooke's law to be able to find these force functions. Without the context of a spring, we might need to do a little bit more work to find these force functions. And so the basic idea that we have right here is still going to hold whether we're dealing with a spring or not. But the only difference is that our force functions might be in a little bit of a different form, because they wouldn't be using Hooke's law, because that only applies to springs. But that's where we'll leave this short video. Hopefully that little example is helpful.